Okay, today we are talking about recursion. Last week we introduced abstract data structures with the stack data structure. We saw what the stack data structure looked like. We performed the basic task on a stack, such as pop. What does pop again? Anybody remember what pop does? What's the function of pop? It removes from the top, right? So pop is the function that removes a value from the stack, right? And how do we add a value to the stack? Brandon? What is the function for that? What's the function? What's the name of the function? Add into the stack. P is there. There's P in the word.
Oh, peak.
No, there's P in the word, but it's not peak. Peak is actually seeing what's at the top of the stack. If you pop to remove, what does a view controller do? What does a navigation controller do? To present a new view controller onto the stack, what does a navigation controller do? In code. So I heard it in the back, right? So you push, right? You push a new value onto the stack. As we go through data structures, please, the implementation might not exactly be there on week one, but know the functions of that data structure, right? What does it do? How can I add to it? What's the terminologies behind it, right? So you push to add, you pop to remove, you pick to see what's at the top, right? Cool? Excellent. But today we're talking about recursion. What is recursion? We're introducing recursion here. On Wikipedia, it says recursion occurs when a thing is defined in terms of itself, right? What does that mean? In programming, in computer science, what that line says is a function could call itself. So I have a function called perform task. Inside that function itself, it also has a call to perform task as well, right? So that is recursion. That is performing the function itself within the function, right? So I call myself within myself. That is the definition of recursion in computer science, right? Where the thing that you define, the function, func, whatever it is, inside the body of the function, there's a recursive call to call the function back, right? To call itself. So you start off with a big problem, right? You start off with a big problem, go get me, or create me a doll. Let me use that example. Create me a doll, right? It could be big, small, whatever it is, create me a doll. There's a next function that says, create me a smaller doll. Inside that function says, create me a smaller doll. So every call to create a doll calls itself. At some point, it needs to stop, right? If it doesn't stop, what happens? Infinite loop, right? So if we don't have what's called a base case, like at some point, like for example, if we count in from 10 and we say just count till whatever, we don't give it that point of stopping, it will continue going until the computer crashes or whatever, the resources crashes. So as Amini says, we have a recursive call. The recursive call is the function calling itself again, but it needs to stop at some point. If it doesn't stop at some point, it will keep calling itself and calling itself and calling itself and calling itself and calling itself until your computer eventually runs out of memory, right? Because every call is memory allocation, and at some point you'll run out of resources, and the computer will crash, or Xcode will crash, whatever comes first there. So we need to have what's known as a base case, okay? So you tell a Mini, go create that doll. At some point, you need to tell a Mini, when the doll gets to 1 inch high, stop. Other than that, she'll try to really get to that nanometer there, right? And she'll keep going until, who knows, 5 billion years. But something else will happen before that. I mean, it'll just be like, I'm done with this. I'm going to something else. So, in recursion, the definition of recursion in computer science, doesn't matter Java, Python, what language you're dealing with, recursion is a function that calls itself. That's a one-liner, very simple to tell somebody if they're asking you what recursion is. In computer science, recursion is a function calling itself. That's it. Yes, sir?
That seems to imply that's the only place that recursion takes place within programming. Is that true?
Within programming, it's also done in mathematics. You see it in art as well. It's everywhere.
Cool.
But in computer science, the definition of it would be the function calls itself.
And that's about it.
That's about it. Okay, so that's the definition of it. Let's go over to our lesson. So the objectives of the day is to write recursive functions, see what they look like. And we will use some very typical situations, very typical functions that introduces recursion as a concept. We'll see what factorial looks like. So we'll use factorial, which is one of the defining ways to show recursion. And we'll also show Fibonacci sequence. Anybody knows the Fibonacci sequence, right? So we'll use the Fibonacci sequence to perform a recursive function on it. Because what happens here, as we said, recursion is a function calling itself. We could take that one step further. When we say a function calling itself, every time the function calls itself, it needs to get smaller or larger depending on what the situation is. If you're trying to count to some number, or if you're trying to create X amount of dolls, right? At some point, you need to get to a stop, right? So that problem is the same problem you're doing over and over again. The things that's different in the problem is the arguments. Am I going up or am I going down, right? How do I change that value, right? With factorial, it's very similar. That's why factorial is used a lot to show what recursion is. Because it's the same formula as factorial, as Fibonacci. We'll see what they look like. But it's the same formula, like you tell somebody, go create a doll. It's the same procedure. They take whatever they take in plaster, they make a mold, same procedure over and over again. What does that remind us of? That reminds us of loops, right? Iteration, right? Be doing stuff iteratively, which we've done from unit 1. But recursion takes it a step further. Recursion says, if you realize there's a problem that could solve itself within itself, using the same structure, the same function, why not use that function and call itself again? It's the same code, same everything, call yourself again and get smaller. As you get smaller, you'll get closer to that base case. When you get to the base case, you're done. So keep creating those dolls, right? Keep creating, let's see, I think Wikipedia has, let's see, find art. One second. In art, right here. Okay, this is what I was looking for. So here we have a photo of Russian dolls, right? So as it's creating the dolls, we see from the left, right, it's a bigger doll, smaller doll, and so forth, right? At some point you stop, right? So this is the same function. Yes, the colors are different, whatever it is there, but it's the same form, right? It's the same form. So you take that same function and you tell somebody, perform this X amount of times until they get to the smallest doll you want in your product line, right? So recursion uses what's known as divide and conquer, right? So you take a big problem, you break it down in smaller pieces using the same formula. For example, with our factorial problem, the same function in mathematics. We take it, we use it until we get to that base case, right? So you say, for example, you're doing 4 factorial, it would be 4 times 3 factorial, 3 factorial would call 2 factorial, 2 factorial would call 1 factorial. At that point, you would stop because you've gotten to 1. 1 is the base case, right? So very similar. So problems like that is solved easier because it's easier to read. It's easier to solve problems like that using recursion. You could solve the same problem using a while loop or for loop, whatever it is, but it's easier to model it, or somebody's able to read your code easier using recursion there if you have a basic formula where it just happens over and over again up to a base case. Okay? So we've introduced what recursion is. We said recursion is a function calling itself. We said recursion is best used where you use divide and conquer. You have a bigger problem. You want to make it smaller by just decreasing some variable or argument that you pass into the function itself until it gets to that base case. And it's very important to have a base case. If you don't have a base case, we'll go into an infinite loop. So the 2 important parts of a recursion function is a base case and the recursive call itself. Those are the 2 things. Let's go back to our lesson here. Before we talk about dynamic programming, we need to talk about what, we'll see why dynamic programming is important to know. it solves a lot of, actually, it's more efficient to write dynamic programming functions with recursion, but we'll see what that looks like. I won't introduce it right now, but after we get through Fibonacci, for example, I'll show us Fibonacci using dynamic programming. Because if you do not use dynamic programming with the Fibonacci function, you end up redundantly calling functions that you've done already. For example, if you created some function that returns 2, why call that function again when you had 2 already? So that 2 gets stored, right, in like a dictionary or whatever. But we'll first introduce what recursion is in code, and then we'll talk about dynamic programming. If we have to come back and talk about dynamic programming, that's fine. I'd rather do that than impose everything on us today. Everybody with me? Okay? But those are the things that ties in with recursion. Okay? All right, so let's go off to Xcode and go to Xcode, create a single view app. Go to Xcode, create a single view application, and call it recursion. I'm not saving it in data persistence. Okay, so we call it recursion, and let's follow along with the examples we have here. Can everybody see in the back here? Yes? Right? Okay, I want to create a simple button on my storyboard so we could call the functions whenever we want to. So go to storyboard, and we're creating a simple button. Nothing crazy here, simple UI button. Drag in a UI button and center the UI button onto your view, and we'll call it perform operations, and we'll center it vertically and horizontally. We'll open up the assistant editor and simply drag an action over to our view controller. And the action, we'll call it perform operations. Okay. And the reason for the button is just to invoke the function as we need to, right? And the reason why I'm not going to playgrounds right now, because what I want to do, I want to show us what happens when we call a function and how that's displayed in Xcode here. Okay, so let's keep going here. Go to my view controller, and let's define a function here. Call it recurse. And we'll simply print hi here, and we'll call recurse. Okay. Xcode does a great job, right? Like, what is Xcode telling us here? Yes, sir.
Yeah, it is recursive.
Right? So basically, as Matt is saying, Xcode is telling us that, Xcode is telling us that this particular function will keep calling itself. Here it's saying all paths through this function will call itself. Meaning there's no point it will stop here. Yes? So our function does call itself, which we want it to do, right? Which is great. But remember, what else do we need? Yes, sir. We need the base case. This function does not have a base case. So here we have the recursive call, but it does not have a base case. So if we go ahead and run our app, let's go run it on the simulator here. Let's go run it on the simulator. Hopefully it doesn't have us restarting our computer. So run it and click on the perform operations. When you're ready, click on the perform. Yes, sir. Oh, I'm sorry. Did I not call it? Sorry. So make sure to call it here. Thank you. So call it and run it again. So call it, run it again, and press on perform operations. Look at that. We'll see at what point it stops. At this point, I run out of memory. It crashed, right? So that should happen to everybody as well, correct? Yes? So we see this exit bad access, right? That's like a memory problem right there. And look in our left panel, in our navigation area here, we see all the calls. All those calls here are on the call stack. We see all the calls says view controller.recurse. Do we see that? In the left panel, do we see all those calls? All those calls here is the function calling itself. And I think it might max out, let's see where it maxes out, right? It maxes out at 100,000 right there, right? What did it max out for you guys? I'm just curious. What did it max? Same, pretty much the same number? Okay. I was just hoping to brag with my 8 cores, but recursion, there's no way to stop that. Okay, so we saw the problem, and here, every time you call a function, the function goes on the call stack, right? We did stacks yesterday. We introduced stacks for a reason before we talk about recursion. That's why I felt it would be a better transition, because we saw stacks. When I say stacks, we know what stacks are. So you call function A, it goes onto the stack. You call function B, it goes onto the stack. Where is B? Where is function B at this point? Is it at the top or the bottom? Top, right? So as you call functions, they go onto the stack. They get returned in the order, not in the order they were placed, but they get returned in the LIFO last in, first out fashion. So if I call function A, I call function B returns, then function A returns. And then my call stack is empty. Everybody with me? Okay, so here we have way too many calls on the call stack here, and our app crashes. Okay? Awesome. So we could do something else. We could say, add a base case to that particular recurse function to make it stop. So we'll say, we'll give it some number. What number do we want to stop it at? Anybody? 7. So we'll give it a number here, recurse number. We'll pass some integer here. And we will say here, okay, that's good. And then we'll pass in 7 here. And here, we need to put some sort of base case. So here I'll say base n, while n is greater than 0. Okay, so here, this is our base case here. So keep calling the function as long as n is greater than 0. Everybody with me? Right now, our warning has gone away, because Xcode does its build process, and it realizes at some point, this function will come to a halt. At some point, we'll get to the base case of that function. So in a recursive call, at minimum, what you have a base case. You need to stop at some point. And you have the actual recursive call. What will make it get to that base case? In that case, n here is the number I passed in. So n is what? What does n represent the first time we call it? What does n represent? 7. So 7 minus 1 is 6. Awesome. Next up, when the function calls itself again, what's the value of n? 6, and 6 minus 1 is 5, and so on and so forth. We get to 3, we get to 2, we get to 1. When we get to 0, does it come inside and print high? No, right? So at that point, we are done. Everybody with me? So that's what we say, divide and conquer. It gets smaller with every call. With every call, it gets smaller until it comes to the base case, and then at that point, it's done. Yes, sir?
So we're kind of ending the value of the input?
Yes, good observation there. So the way you make it smaller is the argument. The argument. Because every time that function, the first time the function gets called, it's 7. Yes?
Yes.
It calls itself again. What is the value? 6. And the way we change that is in the argument. Okay? So the argument is the thing changing the actual value of what n is. Cool? Very good. Awesome. So now let's go ahead and run this. Press perform operations. And here we have our 7 highs, right? High, high, high. And then our function is happy. Our recursive function is happy. It ends. And that is the basic, most basic recursive function you could see and talk about as to like, hey, if somebody tells you like, hey, show me a recursive function. No, you need your base case. No, you need your recursive call. And the recursive call is the function calling itself. Everybody with me? All right. Any questions? And as Matt brought up with the observation there, yes, the way we're making 7 smaller is in the parameter. We say n minus 1. Every time it comes in, n minus 1. Whatever n is, take 1 out of n. Decrement n by 1. All right, cool. Going further here, let's do a second example. Was there a question?
No, I was going to say, because technically, like if you want to kind of make an animation out of that, like not an actual animation, but like let's say on this same function, if I press the button, then I like add an outlet. I can add an outlet and say like if the n is odd, then the color should be blue. If n is even, then the color should be red or something like that. And that would change like the color of the font same time while the after I press the button, whatever. I was about to try it, but that's me.
You could do that, but hold that off for animation when we get to animation. But yes, you could use recursion, or you could use iteration like we've used with like a for loop or a while loop to solve it. It depends on what problem you're trying to solve, but yes, you could solve.
That'd be a quicker way to do it.
Yes.
If I, like, let's say I wanted to press the button or like an enter button, and then that's like a small animation that it changes colors a couple times, and then it'll say so that
Yes, you could do that as well. But as I said, when we get to animation, you'll see the completion block might make it even easier than that to do it. Because there's like a duration on an animation block. There's a repeat property as well. You see what I'm saying? So you don't even need to do anything too much there.
Yeah.
You could just say animate this for duration, repeat yes or no.
Oh.
Yeah, it's beautiful. Okay, so let's keep going here. So the second example we use, we say function here, count down to 0 from some number. Okay. We'll print the current number, and we'll call countdown to 0 again. Countdown to 0, and here we'll say num minus 1. And we come to the same problem. Anybody want to tell me how to solve this one? Xcode is telling us it will never stop. Yes? Give it a maximum number, right? So here we could start off with 10. Well, in that case, we're counting down. And we want to count down to 0. So what do we need to do? What do I need to add to make it stop when it gets to 0? Count down to 0. So you start with some number, 100, and you want to stop when it gets to 0. What am I adding to make it stop? Mel? I need a base case, right? But very good. So here we have the recursive call, and we need a base case. What base case will you use here? What base case will you use?
Can we use the same one from Fibonacci?
Yes, we could totally do that. We could say guard n is greater than 0. Go ahead. Well, in this case, we need to add n 0 as well, because we need to show the 0. Right, so one slight change. What am I doing here? It's not n, it's number. So what does this code say? It says, go into my Okay, Xcode. You know what I want, so type it in for me. I'm going into my countdown to 0. If my number is greater than or equal to 0, go ahead and print the number, call the function again. Right, so if we start off with 10 here, let's start off with some examples. If we start off with 10, let's call the function here. You could comment out the recurse function and call countdown to 0. Let's make it 20. So we count down to 0, number is 20. We come in here, it's 20. 20 is greater than or equal to 0, correct? So we come in here, we print 20. It calls countdown to 0 again. In this case, what's the argument here? What's the value? 19, right? Is it 19 or is it still 20? Yulia, when I call the function again, what's the value? We start off with 20. What's the value on line 36? 19. Right? So it comes, it says 19. Is 19 greater than or equal to 0? It comes in, it goes ahead, it prints 19. And so forth and so on. So next step, we have 18. And then here we have 0. Right? It comes here, is 0 greater than or equal to 0? Yes, it's going to come in and it's going to print 0. Right? And at that point, it gets to negative, and then it doesn't print anymore. It stopped. Anybody sees an issue with that?
I guess you could put a really high number and that still might max out the...
High number is okay. A high number is okay.
What if you start with negative?
Ah! There you go. What if you start with a negative? What happens? Is it still going to work? So it started with a negative. Negative is greater than or equal to 0. Nothing happens. That's fine. Your app doesn't crash. Just make sure that all the cases you check for. Don't just like leave everything works, right? Like check for, will it still work with negative? Yes, the function is called countdown to 0, but what if the person puts -10? Like, will it crash the app? In our case here, it won't because number is greater than, that's false. It just returns the number. Everybody with me? So never just walk out from your application thinking everything is good and then you walk away. Okay, so let's go ahead and run that and see what the result is. Is there a chance? Actually, we'll have chances for you guys to whiteboard with this. So go ahead and click on perform operations. We do count from 20 to 0 as we spoke about. So this is great. It's basically 2 lines of code, 1 line of code, whatever. It gets the thing done. And this is recursion. Let's go into some more defining topics here. We won't do the count up. That's basically the same thing. I want to go into Factorial and really see what's happening there. Because Factorial is one of those, believe it or not, you could get it as an interview question. Say like you go to a startup and you know, they're busy, startups are busy. They're like, hey, we need to give this person a question. You could just happen to get Factorial. So knowing how to solve Factorial is one of the things, like I keep saying, know how to reverse a string without any built-in functions, right? Those are the things like you have to walk into any interview knowing how to do it. If somebody was to ask you, hey, reverse a string without any built-in functions. As we get closer to job search, we'll like do those things like repetitively, but never take any of those for granted. Like, oh, they're not asking us Factorial. You go study trees and graphs and then you're like, oh. Right? All right, so we'll jump into Factorial. Does anybody want to tell me what Factorial is? Multiplying the number, so 2 times 4. So there's an equation, right? So Amini starts off by saying there's an equation. Matt, I thought your hand was up.
I was going to say they multiply it by each number below it.
What is the benefit of it? What does it do for us? What does Factorial give us? Or what does it tell us? Like, why do we use it? Or why was the formula even made in the first place? Right? Combination, right? So we're talking about permutation, right? So given 4 different things, how many ways can I arrange that? Right? Without having some sort of formula like factorial, it's going to be a bit hard there, right? What if somebody comes like, I have 16 different things, how can I arrange that? Or how many arrangements can I have? That arrangement is called permutations. How many permutations of some number or some variation of something can I have? Given 16 different shapes or 16 different colors, give me the possible variations of that 16 colors. With factorial, we just plug the number in. 16 factorial, boom, we get the answer. In our case of 4, let's take it easier here. In the case of 4 factorial, what's the answer? You're being recursive right now, right? Almost. So 4 factorial is? Math quiz, pop quiz. Yes, what is 4 factorial? Boom, in the back, we got it. 4 factorial is 24. You have 4 different shapes. You could arrange them in 24 ways. Okay? Let's take a simple example to see what that looks like. Bless you, sir. Let's go. All right, so we're talking about factorial. And the formula for factorial, what is the formula? N times n minus 1, right? Yes? Back in math class? So that's factorial. The factorial of a number, given of a number n, is n, that number, times that number minus itself, factorial. Bless you. So here we said 4 factorial. What is 4 factorial? So given that formula, what is 4 factorial? So 4 factorial is 4 times 3 factorial. Okay? What is 3 factorial? 4 times 3 times 2 factorial. See that? So we keep calling the same function, right? Correct? Until we get to some base case. What's the base case of factorial? No what? Or 1, right? When you get to 1, we stop, right? Where n is greater than 1. So here we get back to 4 times 3 times 2 times 1 factorial, right? And 1 factorial is 1, correct? At that point, we're done. We're done. We calculate our solution. So we say 4 times 3 times 2 times 1. And as Tiffany said, this is 24. Correct? So this is one of the base cases. Any language, doesn't matter. Most languages will introduce recursion with factorial because it totally defines what recursion does. I have a problem. I'm trying to solve factorial. Every time I call the function, it's the same formula I'm putting in that function. So 4 factorial starts, it calls 3 factorial, 3 factorial calls 2 factorial, 2 factorial calls 1 factorial until the problem has been solved. Let's see that again using the call stack here. Let me grab this. Good, bad?
No, that's good. It's the same thing as what I've seen now.
That's not where I want you, sir. Go where I want you to go, mister. I'll keep it there for now. Okay, so what did we do? This is what we did. Using a stack, we have a stack here, everybody. This is our call stack. My function, we first called, what did we first call? 4 factorial. 4 factorial calls 3 factorial. 3 factorial calls 2 factorial. And 1 factorial, correct? Okay, let us fix that a little bit here. So 4 times 3 factorial. Then we have 3 times 2 factorial. Then we have 2 times 1 factorial, and then we have 1 factorial. It would just return 1, as a matter of fact here. So this would just represent it as 1 factorial because it just returns 1, right? Now this is where recursion comes into play. How many calls do we have on the stack right now? 4. We have 4 calls on the stack. Each of those calls needs to return a value, correct? I'm returning the value to whoever called me. Let's see what that looks like. So here, the top value, or the top value in the stack, called this guy, he needs to return its value, correct? What is the value here? 1 factorial returns its value to 2 times 1 factorial. What is the value returned from 1 factorial? 1. Okay, let's keep going. So 2 times 1 factorial returns its value to this guy. What value does it return? 2. 3 times 2 factorial returns its value to 4 times 3 factorial. What value does it return? 6. Okay, very good. And now we are returning to the last caller. This guy needs to return to his last caller. What value is that? So now we say 4 times 3 factorial, right? If it returns 6, now what do we say? If we say 4 times? 4 times 6, 24. Right? Because that's what the definition says, right? The definition says n times n minus 1 factorial. So it goes ahead, it calls each n minus 1, and they need to return their value. When they return their value, it does its multiplication, right? So this one, we did everything here. We said 2 times 1 is 1. We said 3 times 2 factorial is 6. We said 4 times 3 factorial is? Because 3 factorial is 6, right? 3 factorial is 6. That's what got returned. Yeah. Jahid? Yeah. So that here is recursion and stacks together. Because each recursive call gets pushed onto the stack. We'll see what that looks like in code. That's why I'm using the single view app. So each call we make, it goes onto the stack. When those calls get returned, they have the value. So the first one at the top, we said it's 1 factorial, it returns 1. Second one is 2 times 1 factorial. It's like I'm calling people. I call you to do something for me, right? You call somebody else to do something for you. Then Howard calls you to do something for him. Then you return your information to Howard. Howard returns his information to Amini. Amini returns her information to me. At the end of the day, I get everything that I need. Cool? All right. So let's see what that looks like in code. No, that's fine. Let's stay here. Let's see what, because every call goes on the stack. Remember when our app crashed? We saw all the calls there. That's all on the call stack. Call stack is part of Xcode. Every time you call a function, it goes on the call stack. Everybody? When I say call stack, I'm saying every function that gets called in our project goes on what's known as the call stack. Okay? Functions gets placed onto the call stack. So visually, this is exactly what's happening with our recursive call. Okay, very good. Okay, so let's see. Factorial. And here we'll use the same argument structure we had. We'll say n. In this case, it actually returns a value. What does it return? What type? What data type? An int, right? We're dealing with int here. Very good. So here we need a base case, and we know we need some sort of recursive call. And we said the formula for finding factorial is n times n. And we said factorial is used to find the number of permutations of a given, in this case, number. Okay. But before I go ahead and solve this, let's actually go back. I want to show the permutation part of it and how it actually works here. So if we have, for example, we have some colors here. Right? We have three distinct colors. What's the permutation or what's the factorial of that? What's that? I heard it? 6, right? You can shout it out, it's fine. So let's see what that looks like. So here we have 1. I could start off with a different one. I could say green, red, blue. Then I could go, what's next? Maybe blue? Okay. At this point, we've exhausted green, red, blue, right? Or this one. Let's start off with the. One second, this is not working here. What do we have there? 4. Red is good. Right? So what do we have? 1, 2, 3, 4, 5, 6, right? So we said 3 factorial is 3 times 2, correct? Correct? So imagine doing that for like more than 3 colors, right? So we have the formula there to take care of that for us, right? But basically, this is what we're solving there. How many ways can we arrange those colors? Okay? And this time we're calling the same function again. Let's keep going here. Okay, so we said we need a base case. What's the base case for factorial? We said earlier? 1, right? So here we know the base case is 1. So let's code that out. So we'll say guard n is greater than 1. Else return. Here we need to return something. What value are we returning? 1. Very good. Thank you, sir. Awesome. Now we need to go to our recursive call. We could basically plug the formula in. That's where recursion becomes like way simpler to write. We could just basically plug that same formula into our function and just have a return keyword, and that would be it. So this is exactly what we'll do. We'll say return. We need to call the function itself. So n times factorial n minus 1. Or rather, let's do this better. So this is cleaner to read. Sorry. So this is base case here. Right? So that's the function. We'll test it out. We have our base case. We say we could keep going until we get to 1. When it's 1, we just return 1. In that case, 4, if it's 4, for example, 4 would be, let's model what that looks like. It would be 4 times factorial, what am I putting into the argument? 3. And then 3 would call, exactly, very good. And then 2, and then 1. Yes?
What do you call that if it's already for n?
It would just return what?
But if it's saying n greater than 1, would it actually return the last line then?
It would not call line 46. It would just return 1.
Right, so would it call line 50 in that example?
line 50. So 2 factorial, so it still calls this one, right? Keep that in mind.
Right.
So it wouldn't call, it would just return, it would just return the result of this, which would be 1 here. So this would be 1, and this would be 2, and this would be 6, right? And this would be our answer of 24.
So if that's the case when it's printed, you might scroll all the way to the top of what's printed into the number?
We'll get the number right away because that's the last thing it returns to us is 24. It doesn't return. No, it wouldn't. It would just return, remember, at the end of the day, we're the one calling it. We're the last person to get the answer. Tiffany, right, and class, this is very important. We're the one calling factorial. We're the ones to get the answer last. And the answer we get is the final answer of 24. Okay? In between, 1 will get returned to 2 factorial, and 2 will get returned to 3 factorial. But in our console, what we see is 24. Everybody? Cool. So let us test this out right here and call it. So factorial 4, we'll use 4 here. 4 is a good number. Unused. Oh, the result, sorry. Result factorial. Sometimes I think I'm still in playgrounds. And then just print it here. All right, so let's run that first, and then we'll take a look at what the call stack looks like. So we run it, we click our perform operations, and we get back 24. We don't see, as we said, we're not gonna see 1, we're not gonna see 2, we're not gonna see 6, we'll see 24. Because the caller, the last caller in our diagram here, that last caller is 24. That's us. Everybody with me? Okay. All right, so let's put a breakpoint in a couple places and let's see what's happening. Break up your code like this so you could put a breakpoint on your return statement. No, sorry, this is the wrong function. Right here. In our factorial function, put some white spaces, put a breakpoint at 50, and put one at 52. Well, different numbers for you. And let us go ahead and run the app again. Okay, so click on Perform Operations and take a look at what we have here. So the first call, where are we? We're on line 52, right? Our breakpoint is on line 52. Do we see view controller dot factorial? Everybody sees that in the console? So this is one call. That call is on the call stack. That's call number 1. Everybody sees that? Or the last call in our case here. That's actually the answer already. But let's go keep playing the playgrounds here. So play again. Here, we have another factorial on the call stack. Do we see 2 now? Do we see 2 different calls to factorial? Click the play button again. We see 3 calls on the call stack. So when I say the call stack, this is the call stack. So as you're using breakpoints in your own project and you're looking at some function, when you put a breakpoint, you'll see the current stack, the current flow of your code. What's happening? In our flow here, we're still in the function, and there's still functions currently on the stack. They're not done yet because we haven't gotten our result yet. Let's keep going. And now, where are we? Where's the breakpoint? The breakpoint now is on return 1. So, Greg, for your point, so now that's calling factorial 1. And factorial 1, what it does, it checks, it's like, hey, I cannot keep calling anymore. I'm at my base. Everybody? Right now, we at the last call, it cannot call anymore, and it just returns the result. So if you click on the play button again, the call stack will be empty, everything will get popped out of the stack, and you'll get your answer. So if we click on the play button again, we do get 24. So we drew it and we saw it in Xcode at the same way. Every call gets placed onto the call stack. When the call is returning, it gets popped from the call stack. Here we have 4 calls on the call stack because we're doing 4 factorial. Well, when one gets called, factorial 1 does get called by factorial 2, but it doesn't call factorial 0, for example. It just returns 1. Yeah, very similar to our drawing here. The very top of the stack, this is 1 factorial, right? It just returns 1. It doesn't call 0 factorial. Any questions about that?
So
Yes?
on that return one line, is that just multiplying the result against that one?
Let's go back here. This guy?
Yeah.
Yes.
Sorry,
Line
line 50.
50.
It's
Line 50 returns 1, right? And the other, whatever value it calculated returns to the other caller. It has that value already. And then it always gets multiplied by n, yes. Very similar to this illustration here, right? So 2 gets multiplied by whatever the value of 1 factorial is.
So would that be good practice to return 1 there so that you get...
Not even best practice. You have to know what your base case is. That the reason why we return 1, because 1 factorial is 1. That's why. Okay, very good. All right. With Fibonacci, we'll see it's a different base case. How are we doing? We started at 10:15, right? We good? Good? Okay. So this is this. Let's go to Fibonacci, actually. Okay. So let's talk about Fibonacci, and then that'll be our last example for the day. So Fibonacci, again, is some formula, a sequence of numbers that we saw in mathematics. Some of us probably saw it. But basically, this is a sequence of numbers whereby the number, for example, 2, where n, if n is 2, and you're trying to find out what the Fibonacci number of n at 2 is, you basically need to add the preceding numbers. So say, for example, n is 2. Let's take a different example. Let's say n is 6. If n is 6, n is pointing here. Right? N is 6, our number is 6. What is the Fibonacci value of n at position 6? How do you come about that? You come about that by adding the preceding values. The 2 preceding values. So you add 3 plus 5. 3 plus 5 is 8. If you have to do, for example, 4, if we do n equal 4 here, we go down to 4. How do we get to 3? How do we get to 3, May?
Or do you mean like
Yeah, the Fibonacci sequence, using the Fibonacci sequence at n equal 4, or n is 4, how do we get to the value of 3? How do we get to the value of 3?
the value of 3? So it would be 2 in this case?
It would be 2 plus 1.
Yeah, 2.
It's the preceding, so it's n minus 1. In that case, it's 2, plus n minus 2. In that case, it would be 1. Cool? So that's like the formula there. So any value you want to get, the formula states that n minus 1 plus n minus 2 would get you that number. For example, at position 8, the value is 21 because 13 plus 8 equals to 21. Everybody with me? So that's the basic way you get Fibonacci values. Given the formula n minus 1 plus n minus 2, you could get any number at any point. And it's always the 2 preceding numbers.